We will now talk about sets. What is a set? Well, a set is basically a collection of items or elements. This collection is unordered. Okay, so there is no order when we talk about a set and someone asks us to report the elements of that set. We can report them in any order we want because order makes no sense in the case of sets. One very important point to make here is that no item can appear more than once in a set. So for example, this is not a proper set. Okay, this is not a proper set because one appeared more than once. Okay, now there are two ways of describing the sets. I can basically list all the elements of the set. So if I want to have the set of the numbers between 1 and 5, 1, 2, 3, 4, 5. This is one description of the set. If I wanted to have a set or describe the set of all the letters between A and F, it is A, B, C, D, E, F. This is known as the roster method, where we just explicitly enumerate the elements of that set. However, in many cases, it's not easy to list the elements explicitly. For example, if I want to say all the integers greater than 5, then that set is infinite. And usually we would say, for example, n such that n greater than 5. So this is now known as the set comprehension. We are describing the set in terms, or the elements in the set in terms of a property that they satisfy. So here, the way we read this is that n such that n is greater than 5. Sometimes we also, instead of the colon, we write it as a bar, like this, n such that n greater than 5. Okay? Or sometimes, for a different set is that all the p such that p is prime. Okay, there's an infinite number of primes, and I cannot just list them one by one. And this is one way of describing it. Of course, sometimes we use the roster method to describe infinite sets when it's very clear what we mean. So if I write something like this, 1, 2, 3, ... this is basically the set of all natural numbers. Okay. When we talk about a set, the first thing we need to talk about is that is a specific element or an item an element of that set or not. So we use this notation here to denote that A is an element of a set, or this notation to say that A is not an element of a set. So if I take the set S to be the numbers 1, 2, 3, 4, and 5, I say, for example, 2 is an element of the set S. 5 is an element of this set. However, 6 is not an element of this set. Okay? Same thing, 8 is not an element of this, and the letter A is not an element of this set. Okay. We have very important sets that we deal with in general in mathematics and in computer science, and we have special letters to denote them, and these are the set of natural numbers. So these are the numbers 0, 1, 2, all the way to infinity. Or sometimes we see that the set of natural numbers is just 1, 2, 3, 4, and so on. The set of integers is the set of all whole numbers, positive, negative, and 0 as well. The set of positive integers, it's 1, 2, 3, all the way to infinity. The set of rational numbers, a number is rational if you can write it as the fraction of p over q, for two integers p and q. Okay, so again, 2 is rational, 17 is rational, 2/3 is rational, 1/10 is rational, but pi is not rational. Square root of 2 is not rational. Square root of 3 is not rational, and so on. The set of real numbers, all the numbers on the real axis, right? So if all numbers between minus infinity and infinity, and include the whole numbers, the integers, the rational numbers, all of them. The set of positive real numbers, this is when we talk about all the numbers that are in real but greater than 0. So in some sense, R plus is all the x in R such that x is greater than 0. Okay, so we can describe the set as this. One important set that we always deal with is the empty set. The empty set is a set that contains no elements, okay? And we denote it by this circle with the line through it, or the notation of a set with nothing in it. it's very important to understand that the empty set is a set that contains nothing, and this set is not an empty set. It's a set that contains one element, that is the empty set. Okay, so for example, this is an element of this. Okay, however, the empty set is not an element of this. Okay, so the empty set is a very special set that contains no elements, but it is still a set. Cardinality of a set, or the size of a set, is the number of elements in that set, and we denote it by putting these two bars similar to absolute value. But when we put them around a set, we denote the size of this set. So if I have the set that contains 1, 2, 3, the cardinality of this, or the size of this, is 3. The size of the set A, B, C, D, E, F is 6. In particular, the cardinality of the set, the empty set, again, this is the same as the cardinality of the empty set. It is 0, no elements in it. Okay? Not all sets are finite. It's very important to know this. So for example, in the natural numbers, the integers, these are all infinite sets. Infinite sets, they don't have a specific size, right? I mean, we cannot say the number of elements in them is X or Y or Z. They are infinite, and there are two different types of infinity. We usually distinguish between two types of infinity. There is countably infinite sets, and there is uncountable sets. This is not the subject of this lecture here, but it's a very interesting topic that to think about, or to look into. Because, for example, the sets n and z, the natural numbers and the integers, we call these countable sets, in the sense that we can enumerate their elements, right? If someone tells you, or asks you to enumerate the elements of the natural numbers, you say, yes, I know how to enumerate them. It's 0, 1, 2, 3, 4, 5, and you're not going to miss any element like that. But if someone asks you to enumerate the elements of R, the real numbers, and suppose you start with 0, what is the next number after 0, right? I mean, we don't know. There's no such thing as what's the next number after 0 in the real numbers. So this is uncountable. Again, this is not the subject of this lecture, but it's very important to keep in mind, not all sets are finite, and infinite sets, there are two flavors of them. One important notion we talk about when we talk about sets is the notion of a subset. So if I give you a set, and I take some elements from that set, then I form a subset. Okay, so we say that A is a subset of B, and we denote it by this symbol here. If for every x, if x is in A, then it must be in B. Okay, look at this implication. We're saying if it is in A, it must be in B. In other words, all the elements in A must be elements of B. But not all the elements of B need to be elements of A. So for example, if B is the set A, B, C, D, and for example, AB is a subset of B, right? Because every element in the set AB is also an element of B. The same thing, A, B, C, D is a subset of B. One element as well here is a subset of B. In particular, the empty set is also a subset of B, because every element in the empty set is an element of B, because there are no elements in the empty set. So it really satisfies this quantified formula here. Okay, so when we look at a subset, just take any set of elements from B, and then you form a subset. In particular, if you take no elements from it, which basically gives you the empty set, that's also a subset of B. The power set of a set is the set of all subsets of that set. So if you give me a set A, the power set of A is the set of all subsets of that. So if we look at this, set that contains 1, 2, 3, then the power set of this is the set of all subsets of 1, 2, 3. So the subsets of 1, 2, 3 are the empty set 1, the set that contains 1, the set that contains 2, the set that contains 3, the set that contains 1, 2, 1, 3, 2, 3, and 1, 2, 3. These are all the subsets of the set that contains 1, 2, 3. You can check and you will not find any other subsets of 1, 2, 3. If we look at the empty set, what's the power set of this? The set of all subsets of the empty set. Remember that the empty set has a subset, that is the empty set. So the power set of the empty set is the set that contains the empty set. Okay? In addition to subset, we talk also about proper subsets. So when we talked about subset, remember that 1, 2, 3 is a subset of 1, 2, 3, right? But this is not a proper subset because they are equal sets, right? So if I want to talk about proper subset, it basically says that I have a subset of the elements, but not all the elements in that subset. So if for example, 1 is a proper subset of 1, 2, 3. 1, 3 is a proper subset of 1, 2, 3. The empty set is a proper subset of 1, 2, 3. However, 1, 2, 3 is not a proper subset of 1, 2, 3. Okay? So for A to be a proper subset of B, A has to be a subset of B, but also B has to have at least one more element than A. Last thing I want to talk about in this lecture is a very important graphical description of sets and their relationship, which we call as the Venn diagram. The Venn diagram is a very simple notation or graphical representation that when we are given a set of sets, we can describe their relationship. Usually, when we talk about sets, there is a universal set, which is the set of the universal set of all the elements that we are working with. So for example, if we are dealing with sets from the set of integer, then the universal set is the set of all integers and so on. So if I want to describe the Venn diagram of sets and their relations, usually we denote by a rectangle the universal set, for example, all the integers. And then we denote by circles and their relationship, these subsets. So for example, suppose I want to denote the set or the relationship captured by A in union B. So usually, again, we will draw a rectangle with denoted by U. This is the universal sets. And here is set A, and here is set B. So this is A, and this is B. And we shade the area that corresponds to the set we are interested in. So for A union B, the area that corresponds to the union of these two sets, for example, is this. Okay, so what is the union? Is the set of all elements in A and B. We will get to this next. Okay, and if I want to draw, for example, the intersection of two sets, which we denote by like this, which is what is the set of all elements that are both in A and in B. I can draw a rectangle, say here is the universal set, here is A, here is B. These are the two sets, A and B. But the intersection is the set of elements that are in both A and B. So it's this region here. Okay? This is what we call the Venn diagram. And when I talk about these operations in the next lecture, I will actually draw the Venn diagram of each one of them. Okay? But again, just keep in mind that the Venn diagram is we draw usually a rectangle for the universal set, which is the set of all elements we are interested in or concerned about. And then we draw individual sets as circles, and then we shade areas that correspond to the quantity we are interested in.